Let's say you want to own a chip fabrication plant. No problem at all, just a little detail. There are only a handful of buildings on Earth that can build the chip inside your phone, and every single one of them is already owned by one company. The United States, South Korea, Europe, and Japan have thrown over $350 billion at this problem, and none of them have caught up. And the reason why is going to change the way you think about every device you own and every dollar you spend on technology. But to understand that, first you need to understand what you are actually trying to build. Not all fabs are equal. The industry splits into 3 tiers by the size of the transistor they can print, measured in nanometers. A legacy fab, the chip in your dishwasher, the controller in your car's braking system, costs $1 billion to $3 billion to build. It's profitable and reliable, but the technology is completely commoditized, and China has built hundreds of them. A mature fab in the 7 to 10 nanometer range costs $5 billion to $10 billion. And this is where Samsung, Global Foundries, and Intel's older facilities compete. Enough for most consumer electronics, but not the leading edge. Then there is a leading edge fab, 3 nanometers and below, TSMC's N3 and N2 nodes, the facility that builds the processor inside every iPhone, every MacBook, every NVIDIA AI accelerator in the world. And the cost to build one runs $20 billion to $30 billion before you turn the lights on. Most people assume the $20 billion is the barrier, but it's not. The barrier is the machine. To print a 3 nanometer transistor, you need an extreme ultraviolet lithography machine that fires a laser 50,000 times per second at a tin droplet the size of a human cell, turning it into plasma and generating light at a wavelength of 13.5 nanometers. And that light, bounced through mirrors so precise they would be the flattest objects ever manufactured if measured at the scale of Germany, is what carves the circuit. There's exactly one company on Earth that makes an EUV machine, and that is ASML in the Netherlands, where one machine costs $350 million. A leading-edge fab needs 8 to 15 of them, and every single one comes from a supplier with a 2-year waiting list. The United States banned EUV exports to China in 2023, and China has spent an estimated $50 billion trying to build its own, and it has not succeeded. To understand why, you need to understand one man. Morris Chang was born in China in 1931. Educated at MIT and Stanford, he spent 25 years running semiconductor operations at Texas Instruments before the government of Taiwan gave him $220 million and one instruction: build a foundry that makes chips for other companies, no products of its own, just manufacturing for hire at world-class level. Chang invented the pure-play foundry model. Before TSMC, every chip maker designed and built its own chips. But after a company with no factory at all could design any chip it wanted and outsource the production entirely, which is exactly how Apple, NVIDIA, AMD, and Qualcomm all exist as fabless chip companies today. TSMC now serves over 500 customers, posted $69 billion in revenue in 2023. Its market cap has crossed $1 trillion. And the model Morris Chang built has never been successfully replicated by anyone. But what nobody expected was just how brutally expensive it is to run that model at the leading edge, and what it costs when the numbers go wrong. Here is every line item on your fab. Land and site preparation, ultra-pure water in the millions of gallons per day, vibration isolation, seismic stability in a clean room with less than 1 dust particle per cubic foot of air runs $500 million to $1 billion before a single wall goes up. Construction and clean room build-out adds another $2 billion to $4 billion. Lithography tools, EUV machines, at $3 billion to $5 billion, plus ancillary equipment like etch, deposition, inspection, and metrology, add another $5 billion to $8 billion on top of that. Utilities infrastructure runs $1.5 billion to $2.5 billion because a leading-edge fab consumes 100 to 200 megawatts of power, the equivalent of a small city. Workforce adds $1 billion to $2 billion because you need 4,000 to 6,000 engineers and technicians, and 2 full years to ramp before the facility reaches target yield. Total upfront runs $20 billion to $30 billion before you produce a commercially sellable chip, and then annual operating costs add $3 billion to $5 billion per year, with depreciation on a $25 billion facility running another $2 billion to $3 billion annually, which means you are burning $5 billion to $8 billion a year just to exist. And this is where it gets interesting, because the number that actually destroys most fabs is not anywhere on that list. It is not a cost you can budget for, and it is not a problem you can engineer away before you start. It is called yield, the percentage of chips on each wafer that actually work. It starts below 50% when a new process node launches, and TSMC spent 4 years getting N3 to commercial yield. meaning more than half of every wafer they ran during that period came out as garbage, expensive, meticulously manufactured garbage. At $17,000 per wafer, a 40% yield loss is $6,800 in pure waste per disk, and at 100,000 wafers a month, that is $680 million in wasted material every single month for years, and you cannot run more wafers to compensate because the machines are already running 24 hours a day with an unplanned EUV outage costing $1 million to $5 million in lost production per day. Now, remember what we said about TSMC, a company running these same machines at this same scale posting a 54% gross margin. We'll get back to how that is possible in a moment, but first we need to talk about every company that tried to solve this problem and failed. GlobalFoundries spent 3 years and $1.4 billion chasing 7nm production before canceling the entire program in August 2018. They could not get the yield, the investment was written off entirely, and GlobalFoundries has not competed at the leading edge since and never will. Intel's story is worse. $100 billion in planned capex across Arizona, Ohio, Germany, and Israel, and the Ohio facility has held its groundbreaking ceremony twice without breaking real ground. Germany is delayed 2 years, there are no external leading-edge customers, and the company is burning $7 billion per year in foundry losses, with the stock down 60% from its 2021 high. And then there is China, where Beijing has poured an estimated $150 billion into domestic chip manufacturing since 2015. Semiconductor Manufacturing International Corporation reached 7nm production in 2023, a node TSMC mastered 5 years earlier. But without EUV access, SMIC uses multi-patterning techniques that require 30% more tool passes per wafer, making each chip 40% more expensive to produce. They can make it, but they cannot sell it at a price anyone will pay. And this leads to something even more surprising. TSMC's gross margin in 2023 was 54%, higher than Apple's product margins and higher than most software companies. And it comes down to 3 mechanisms, none of which are what you think. First, pricing power from monopoly. NVIDIA's H100 is physically impossible to manufacture anywhere else at specification. TSMC charges $10,000 to $15,000 per wafer, and the buyer pays it or waits 2 years for an alternative that does not exist. Second, customer-funded capacity. When Apple designs a new chip, it signs a supply agreement before the chip exists, including deposit payments that partially fund the fab expansion required to produce it. Apple committed an estimated $3.4 billion in 2023 for chips that would not ship until 2024. TSMC builds the capacity using the customer's own money. Third, the learning curve. 37 years of compounding process improvements, every percentage point of yield gained, and every hour of downtime eliminated, building into a cost advantage that no new entrant can replicate. This is the answer to the question we opened with. Why can't anyone copy TSMC? Not because of the money and not because of the machines, but because 37 years of compounding institutional knowledge is not something you can buy, subsidize, or replicate on a government timeline. The gap is structural, but there is one risk that even TSMC cannot engineer away, and it is the one that should concern you most. TSMC produces over 90% of the world's most advanced chips in Taiwan, an island that sits 110 miles from mainland China, a country that has publicly stated reunification as national policy, and the United States, Japan, and the European Union have all formally classified TSMC as critical national security infrastructure. In a conflict scenario, not an invasion but a naval blockade, a strike on key facilities, or simply a credible threat of either, global supply of AI accelerators, smartphone processors, and advanced military chips stops simultaneously. TSMC cannot move because the process knowledge, the workforce, and the entire supplier ecosystem all exist in Taiwan. You control nothing that matters. The geography controls it. You have built your fab, $25 billion in capex operational, and here are your 2 scenarios. Optimistic, yield at 85%, 100,000 wafers per month at $12,000 average selling price. Gross revenue of $14.4 billion per year. Operating costs of $4.5 billion, depreciation of $2.5 billion, and a net income of approximately $7.4 billion, with a payback period of 3.4 years, and this is TSMC's actual performance at mature high-yield nodes. Realistic, yield at 65% for the first 2 years, revenue drops to $9.4 billion, operating costs rise to $5.2 billion because low yield wastes more materials per good chip, net income falls to $1.7 billion, and your payback period stretches to 14.7 years. years. And this assumes you already have customers, which assumes you have already solved the yield problem. The difference between a good year and a bad year is $5.7 billion. And here's the part most people never think about, the part that connects your wallet directly to everything we just covered. Every major government on Earth has spent a combined $500 billion over 5 years trying to reduce dependence on TSMC. The AI chip shortage that sent NVIDIA's stock up 800% in 18 months was not a design problem, but a manufacturing problem. And every AI model you have used, ChatGPT, Claude, Gemini, runs on chips made in Taiwan. When TSMC raises prices, and they raised wafer prices 6% in 2024, those costs flow into every device and service you pay for. Every AI subscription, every smartphone upgrade, every server your company runs in the cloud. You are already paying for the monopoly, and you are already funding the geopolitical risk.